Crypto Robots, Exploring Modern Robotics. Why crypto, you ask? We're not sure either. A lecture series exploring history, theory, and practice with demos. Presented by Swarf Industries, a science and technology company building the world's largest pile of Swarf. This series is hosted at Crashspace, a hackerspace in Los Angeles. Crashspace is a 501c3 nonprofit and a member-funded space for building, making, hacking, and meeting new people. Check out Crashspace online at crashspace.org. That's me on the forklift. I'm Kyle Cawthorn. I built the CHARLI robot at Romella at Virginia Tech, designed the Slick 4 East lift system for Falcon Heavy at SpaceX, and architected the development loop at Hyperloop One. I'm an avid photographer and a burner. Check out my personal website at kylecawthorn.com. Alright, now we're recording. Cool. So, I'm Kyle. I'm going to give the presentation on crypto robots now. I kind of had to go back and re-record some of this because the footage that we got at Crashspace was a little, lacking. So, I'm just going to step through the presentation here, and we're going to kind of cut this all together into a supercut of some sort, and maybe I'll show some parts from the Crashspace presentation, but probably gonna leave some of that out because, well, it's a little shaky. I used to work in the robotics and mechanisms lab at Virginia Tech. We developed CHARLI, the humanoid robot there, which is a full-scale humanoid robot. You'll see that in the intro. And we did a lot of work with the kinematics, the servos, the design of the system, and tried to do some human-robot interaction studies later on in the lab. Most of my work there was as an undergraduate, so I wasn't doing, graduate level paper writing a lot. Most of it was hands-on development work, and that'll kind of reflect in some of the demos that I give and some of the history and practice that I go over. But you'll also see some other guest speakers that will give a different perspective, sometimes more academic, sometimes more hands-on. Really depends on their own experience. So the resource page for this lecture series is at swarf.io/robotics. That's SWARF.io. And if you'd like to contribute to the series or have a question for me about any of the subject matter covered in any of the talks, just reach out. My email address is me@kylecawthorn.com. Also, this lecture series is given at Crashspace in person, which is a hackerspace over in Culver City. Their website is www.crashspace.com. So this is the first talk, Intro to Robotics, and what it mostly goes over is kind of the history of robotics, and gets into some of the detailed stuff in terms of just sort of surveying the whole field. It's kind of hard to pin robotics down in one specific spot, so this is a big, broad discussion of everything, and we'll get into more depth as we move further forward in the lecture series and we get into individual topic lectures where we'll go into a lot of detail, so hopefully it's valuable to both experts and people who are new to the subject. But there is the subject matter is presented at an assumed certain level of technical competence, and if you're not quite there yet, follow up with me afterwards, and I can give you some pointers on where to get some of the more basic beginner stuff. So it's sort of for everybody, but if you do have some technical background already, hopefully it shouldn't be too basic. Okay, so this talk covers kind of what robots are and defines them via the history of robotics, and some basic definitions. Then we get into academic disciplines, what kind of coursework you would see leading into a robotics career, basically which fields, disciplines, theories that you need to understand in order to apply and build these complex systems, kind of what the common components are. So that would be things like accelerometers, motors, servos, electronics boards, microcontrollers. Then we get into the design tools that you use to develop the systems and the components, so things like CAD, finite element analysis, CFD, board design tools, simulation tools, that kind of stuff, maybe in development environments for software. And then I'll go over polar plotter project that I'm working on that kind of incorporates a lot of these concepts. So that should kind of give you a good feel for an example project that you could carry out maybe after having completed the lecture series. And we're going to work with that sort of as an example in an ongoing way. I'll try to incorporate a lot of the things that we go over. So robots, what are they? That's a big question. Robots are a type of tool that have been used for centuries. More recently, they've grown very varied, and so we're going to go over the history, and we'll start off with a quick definition. It's complicated. So a robot is a machine that resembles a living creature in being capable of moving independently and performing complex actions. Now, that's the Merriam-Webster's dictionary definition of a robot. That's not necessarily a very good one. A lot of people think that they have to be autonomous in some way. Many people think that there needs to be a microcontroller and some sort of closed-loop control going on. But the definition is partially culturally defined in whatever the pop culture society current thinking of what a robot is, and it's also defined somewhat in academia, and the term is used very loosely. So you'll see things that have no microcontrollers called robots, and you'll see things that are just a bunch of boards plugged together called a robot. And I kind of like to think that there's some electrical aspect, there's some mechanical aspect, and there's some software aspect that work together to give it some sense of it's more than just like a mechanism, and it's more than just a computer. We're going to get into a brief history of robotics. As you can see here, robots fall over a lot. Historically very accurate as far as this presentation starts off. These are robots in the Darpa Robotics challenge, and you can see that standing up is hard. Again, robotics is a very budding industry and academic research field. A lot of the complexity has only recently reached a level where you're starting to mimic human behavior in a real way, and so people are still struggling. And it's very interesting because right now is where you're starting to see some of the breakthrough technologies that'll really shape robotics for the next decades start to really get developed in the labs as people are attacking these problems head on to try and deal with bigger and more complex situations in a more real world for these robots. They've been really confined to the lab until recently, and it's cool to see them start to break out of the lab. So let's kind of go through where they all started and how they kind of got to where they are. So the very first robots, and this is in prehistory Norse mythology, were basically big clay automatons in legend. So there were this concept of artificial servants and companions in the legends of Cadmus, which is like ancient Greek history, and the idea was that these dragon teeth would be sewn into soldiers, which was pretty crazy if you think about back then, like, living things and things that were artificial weren't really married yet. So then kind of further in, you get these things called Mokurukalfi, mist calf, and this was a big clay monster made by Jotuns as a second or substitute for his duel with the god Thor. This god that was battling Thor made this big clay giant as a stand-in for him, and as it turns out, Thor's servant hacked him to pieces, so it didn't really go very well. The first robots weren't that effective either. So let's jump forward to 1770, because nothing really happened between Norse mythology and 1770, as we all know. And we'll take a look at the next robot that was pretty cool and sort of captured the societal imagination, and that's the mechanical Turk or automaton chess player. So this Turk was a robot that played chess. Now, what was interesting about the Turk is that it wasn't an automaton at all. It was a guy in a little chamber under the table moving the pieces around. And it fooled a lot of people for a very long time. In fact, its secret was kept for hundreds of years. Eventually, and the device got passed on to multiple owners who used it to impress audiences around the world. Famous figures famous chess masters operated it, and it was displayed to people like Napoleon Bonaparte, Benjamin Franklin. Like, it was really high society to get a chance to play against the Mechanical Turk. And now Mechanical Turk is sort of a ubiquitous term for um, like kind of rote tasks performed by individuals online who are sort of doing it for very low money. It's kind of it's been used in the tech realm as a way of sort of like Uber drivers or people who go do tasks for you, like TaskRabbit. They'll call those endpoint people that they use to do tasks Mechanical Turks. So Mechanical Turks are kind of one of the first automatons, but there were a lot. There were many of these little statues that the aristocracy would commission that would be like a bird singing, or a man that would write or draw. And they were these commissioned art pieces very early on. They didn't really have practical use, but they were very cool and impressed everybody's friends, and so they were built early on by artisans and inventors. Moving into the 1820s, so jumping forward about 50 years, you start to see their big calculation engines get built. And so this was kind of the mechanical calculation side of things, like pre-computers. A difference engine, in this case, Charles Babbage came up with one of the first mathematics machines that was programmable. And Lady Ada was the one who programmed it. So anybody who's a big fan of Lady Ada and her contributions to early software programming, they were doing that on this difference engine. And the difference engines were used to calculate things like, you could calculate trigonomic functions, logarithms, polynomials, things that you used for stuff like, you might do ballistics with it. You might do, you might make a curve to try and figure out some astronomical quantity, or calculate, the digits of pi to some high precision, right? You could also compute tables of numbers, and then you could have these lookup tables that people could use, kind of like slide rules used to be used. So they were immensely useful as a tool, but they weren't at a stage where they could really like compute any real-time data. Everything was put on these punch cards or tapes that were fed into the machines, and then they would compute based on that input. So then you start to see really pop culture starts to take to the idea that these machines could be servants. And Karl Kapek, and I might be pronouncing that wrong, a Czech author, made this book play called RUR, or Rossum's Universal Robots, and that's where the term for robot was coined the very first time. And basically it meant slave or serf labor. And hard work or drudgery was kind of what the robots carried out in this play. So the idea of a robot is sort of tied to the idea of a slave very early on. And that sort of, you see that theme continue as time goes on. People always see robots as servants and as tools for humankind to progress and sort of replace like labor, essentially. So then in the 40s, you start to see computing applied to the war effort. And that's when vacuum tube switches come around, and you start to see these vacuum tube computers get built. So ENIAC was built in 47, and it was a Turing complete digital computer that was used to solve a ton of different numeric problems, was programmable, and was used to come up with these artillery firing tables for the U.S. Army in their ballistics research laboratory. And so the supercomputers that spun out of the ENIAC system were used for all sorts of different applications, including like design of feasibility of thermonuclear weapons, all sorts of different very cool applications. And that's where you started to see more towards the robotics applications that we have in the modern era. Then, again, robots are starting to really make their way into society at this point, and Asimov comes up with his seminal work, I would say. I'm a robotics guy, so I think it is. But he made this collection of short stories, I, Robot, and basically came up with what are the 3 laws of robotics. So a robot can't injure a human being or through an action allow a human to come to harm. A robot must obey orders given to it by human beings except where they would conflict with the first law, and a robot must protect its own existence as long as it doesn't interfere with the first 2 laws. So those 3 laws of robotics were what Asimov proposed in this book, I, Robot, but they're not really practically implemented. Most robots don't really have a sense of self or understand what harm is to a human or to themselves. A lot of robots are very carefully designed to be safe, but they don't really have any cognition to where they could really decide what a safe action is. There's rules baked into them normally that keep them within safe operating bounds. Some robots are pretty dead reckoning, though, and couldn't even recognize if they're putting a human themselves in a dangerous situation or trying to figure out what their own existence is in the first place. Where you might start to see the first application of these rules or similar rules is in artificial intelligence. So we're starting to see a movement in sort of the hierarchies of the engineering aristocracy where people are starting to become afraid of the potential of AI. And so you'll start to see people try and make ground rules for what AI can do, what it's allowed to mess with, so that it doesn't accidentally go and, decide to cut a bunch of people's power or, mess with people's banking, things like that. In 1955 is where you really start to see some amazing breakthroughs in computing. So the MIT Servo Mechanisms Lab takes a big machine that is used in manufacturing of, war weapons like tanks and aircraft. That's called a mill, and these mills have been traditionally, mechanically operated either by hand, by turning hand cranks, or there have been mechanisms that are set up to sort of carbon copy other parts with cams and followers and things like that. And so they decided that in order to sort of create complex curvatures that they needed for things like wings or joints, things like that, they wanted to try to make a machine that was controlled by a computer. And so there was this lab was directed by Gordon S. Brown, who was then an electrical engineer at MIT, and he decided that for fire control for guns, they could apply some of this stuff to machines as well. So kind of in the 1940s and 1950s, they got a hold of a computer called Whirlwind 1, and they used that computer to develop something called the Automated Programmed Tool Language, which eventually became the G code that a lot of you might know and love from 3D printing. Developing that programming language and implementing it on a machine revolutionized manufacturing overnight. You saw computers brought into shops across the world, and automated machines that could do complex curvature very quickly. And this changed the way that America was producing its machines and equipment, and eventually grew to international movement. So aerospace was really one of the first big adopters, but you saw it in all industries really is use of code in order to control manufacturing equipment. The other interesting side note with the Whirlwind 1 computer is it was integrated into the Sage supercomputer, which eventually was a prototype kind of for the ARPANET, which DARPA developed, and as some of you might know, eventually turned into the internet. And so the same supercomputer that they developed the automated programming tool language on, they developed, was like an early archetype of the internet. And I find that pretty amazing that you can all sort of tie that back to one small experimental phase in U.S. research, and that all of those really cool things spun out of that, like a single computer development program. Okay, so kind of the next advance you see that's pretty major is in the 1960s. In 61, Joseph Engelberger, who's called the father of robotics, develops Unimate, which is the very first industrial robot. It's patented in 54, and George DeVol is the inventor, right? And so Joseph Engelberger kind of has the foresight and business acumen to get this into use. Basically, Unimate was first employed in a General Motors assembly line for their automotive plant in New Jersey, and it was used to transport die castings from an assembly line and welding them onto auto bodies, which is a very dangerous task for the workers because they could be poisoned by the fumes or potentially lose a limb from dropping these heavy castings, or being in the wrong place on the assembly line at the wrong time. So these robots were really doing a very dirty, dangerous job, which is something that robots are particularly good at, because if they're damaged, you don't really lose much. But humans, on the other hand, are squishy meat bags in many ways. In 1964, you see the development of BASIC. BASIC is the first interpreted language, if I'm correct about that. And so it's a sort of a what you see is what you get. You can type things into a command line and then hit a button and they'll compile at that point, at which point they will run. So it's a very simple language for programming, and it was developed at Dartmouth by Kearney and Kurtz. And so this language became very widespread on some of the early computers, like the Atari 2600, and some of the very early like Apple computers. So it was a lot of people's first foray into programming for people who weren't in large research labs. And BASIC is still, to some degree, used as a teaching language, normally archaically. A lot of people learn on Python now. You can see this XKCD that kind of explains the difficulty of languages and basics right there at the beginning. There's not a lot of really complicated application of BASIC. It's more used for teaching now, if anything. So, moving on, in the 1960s, so 1966, you start to see mobile robotics develop. Shaky the Robot is the first general purpose robot that is able to reason about its own actions. So basically it takes in sensor data and puts out like motion pathing. And so Shaky was developed by the Stanford Research Institute in the Artificial Intelligence Center there, and it was used to develop things like the A-star search algorithm, the hue transform, and the visibility graph method, which are some fundamental research, basically fundamental algorithms that are used in robotics for a long time, and built upon to get to some of the more advanced methods we use today for mobile robots, like simultaneous localization and mapping, mapping of interiors with cameras and LiDAR, things like that. And as you can see in the picture here, it's pretty big. It can barely get around this lab that has a nice clean floor. And there's also, those nice gentlemen in ties. Above their head is a large tether that goes back to the computer that actually drives this robot. So it's not a self-contained autonomous robot. It's sort of attached to a big computer that crunches the numbers. But it was one of the very first robots that had computer vision. Like you can see its camera, and it was able to, move based on this sensor input, which was something that was new for robotics at the time. So then in 79, you saw the founding of the GRASP lab, which GRASP is the General Robotics Automation Sensing and Perception Lab at UPenn. And so this lab is actually in the modern era developing very cool quad rotor control algorithms, as well as ways of having them cooperate with each other. So they've really been pushing the boundaries in terms of what you can do with these flying sort of unidirectional aircraft. And They also have been writing some really great code for years. The lab that I worked in, Robotics and Mechanisms Lab at Virginia Tech, teamed up with them to work on code for their soccer playing robots in the RoboCup competition, and you can see them working on a lot of control of large groups of robots, as well as like cooperative robot behavior. In 1979, you also saw the founding of the Robotics Institute in the School of Computer Science at Carnegie Mellon. Carnegie Mellon would go on to be one of the more advanced robotics labs. They would work on space robots, medical robots, industrial systems, computer vision, artificial intelligence, and a ton of different robotic systems have been developed at Carnegie Mellon over time. They've contributed to many different fields of robotics, essentially. In 2012, they have about 500 people working on robots annually, and the NREC lab spun out of the Robotics Institute at Carnegie Mellon. And so you see a lot of rover technology developed there, a ton of different industrial systems robotics and computer vision tools. It's very, like the CMU cam is one that comes to mind of one of the really cool tools that they developed that has been used across research academia as well as in industry. That eventually turned into Pixie, which is like a nice little integrated computing power camera that can just output some simpler data, so that you kind of have at the point of application all the computer vision processing going on. So those are some interesting sort of things that have been developed at Carnegie Mellon and the Robotics Institute, and that was kind of a cool thing to get founded in the 70s. In 1980, you see the Turtle robots as part of the Logo programming language developed, and they're really what allow early computer science researchers to have a platform to test out different ways of programming these mobile robots. It's a low-cost way for students in academia to enter and try out things. You can see here the Logo robots or the Logo programming language was used to program these little turtle robots, and they had a pen in them, and so they could do these like cool spirograph drawings just by giving them a programmed path to follow. And variations of these Logo turtles are still used today. They're very interesting as a platform for educating people on both programming and also like simple robotics, driving motors, things like that. So in 81, you see the SCARA arm, or the Selective Compliance Assembly Robot arm. So XY positioning for picking up items and placing them is critical in industrial application, and an arm with parallel chain of links that are all rotating sort of in the same cardinal direction, or about the same cardinal axis, but in like a plane, is seen as very valuable because it allows you to have a wide range of motion that stays flat in a plane. And normally there's a up-down translation on the end effector, and it's very rigid, and it has good repeatability, and it's fast. And so these arms get a lot of application in silicon processing, things like that, and make their way into industry. So in 1986, you see the development of E0, which is Honda's very first foray into building a humanoid robot. And it's really just a pair of legs. It's very shaky, it walks very slowly, but it's starting to figure out how to mimic the way humans locomote and be able to deal with some of the complex terrain and spaces that humans inhabit. Later, Honda will end up developing many robots towards a humanoid, and they'll end up developing one of the first really successful humanoids, Honda Osimo. And you'll see that sort of over time. Then in 89, you start to see multi-legged robots come out. So this is a 6-legged walker called Genghis that was developed at MIT. It was very quick and cheap to build. It used 4 microprocessors, 22 sensors, and 12 servo motors. And you can see its gait is a little funky, but it was fast and cheap, and that was something new for robotics. At the time, they were very expensive and took a very long time to develop and build. And so you start to see components become available that allows roboticists to really get in there quick and end up with something that has enough control and strength to do something interesting. without spending decades developing these robots. In 1992, you see the beginning of the first robotics competition. I got my start in robotics in first. It was a brand new thing when I was a kid, and it really gives you a great introduction to, team effort to build mobile robots. And they build these teleoperated robots that weigh about 120 pounds. There's a brief autonomous period, and then there's a competition period. And there's hundreds of teams now that come into these regional events and compete. Their robots try and each tackle the challenge in their own unique ways. There's this 6-week design period that's very short and fast. It's been going on for almost 30 years now, and it's a really great way to get introduced to all the different control methods and components that you might interact with. And there's also great opportunities for engineers to mentor youth that are interested in getting into engineering. It was started by Dean Kamen, who is a medical device developer and also is the inventor of the Segway. And I would say it's definitely a great introduction to engineering for kids. I'd highly recommend getting involved in first if you're interested, and you can check out their website. So in '93, you saw the P1 developed. So P1 is the first Honda robot that has arms and legs, and it looks an awful lot like a human with a box for a head. P1 eventually would develop into Osimo later on in around 2000, but P1 was really this breakthrough in that you had this autonomous legged robot that could manipulate things with arms and hands, and so you're getting very close to mimicking human action. In '97, you see Sojourner, which is the first mobile probe to go to Mars, and this is a picture of it from the insurance camera that was on the lander to make sure that it actually got off the lander. So we started our Mars exploration pretty soon after modern robotics really got off the ground. And, as you'll see over decades, we sent more and more of these probes that have really given us a lot of information on what's going on a planet that is millions of miles away. So it's very interesting, the design case there. In 1998, the same kind of tech that's sending us to Mars is really made available to kids in the form of these Lego robotics kits. So there was a series of microcontrollers that were developed in the MIT Media Lab that would eventually get coupled with a really simple programming language and Legos to build a kit that kids could use to build their own mobile robots. I grew up on these. They're super easy to use. You had motor bricks and sensor bricks and a controller brick, and you could program it in a simple visual programming language that taught kids really bad programming habits, but still allowed them to see what a do-while loop would do, or come up with a line-following robot that could do different things based on what the sensor input was. And so they're really a great opportunity for kids to learn robotics. And there's modern versions of these kits as well if you're interested in getting up and running very quickly on building a little mechanical robot that has sensor feedback. They're great. And they're pretty low cost. The kits back then were about $200. I think they run $300 to $400 now, but they're available online. You can get them on Amazon, and they're a great introduction to robotics for kids. In 2005, you start to see some more complex dynamic robots come out that are unstable in a static configuration, but can walk and move in a dynamic configuration, and that has to do with how fast the controllers are getting, and how small and dense the compute power is, and the actuator power density is. And so you see Big Dog come out of Boston Dynamics. So Boston Dynamics is a spin-out company from MIT, and they worked with JPL and Harvard University, and were funded by Darpa to build robots that could carry payloads for the warfighters. And so Boston Dynamics develops Big Dog, which is capable of walking, and it won't fall over if it sees like erroneous input. So if somebody kicks it or it bumps into something, it can still sort of react to that. And one of the big, they made huge advances in hydraulics, and they also made huge advances in what's called series elastic legs or series elastic actuation, where essentially they would have a spring in series with some actuators, and that would allow them to take impacts and simplify the control code to where they were mostly focused on dealing with the force input rather than having to simulate in real time the contact, the dynamics of the contact interaction with the ground, which is actually very complicated and hard to quickly compute, or at least it was at the time. This is back around when I was starting to get into college and work on humanoid robots that tried to deal with some of these simulation and output control loop tasks, and it was very challenging back then. Like, the computers just weren't quite there to where you had enough processor overhead to quickly compute these things and then send command signals back to the legs in order to close the loop before you would fall over. And so Boston Dynamics managed to pull it off very early, and they're one of the, I would say, one of the control leaders in terms of navigating rough terrain with legged robots. Also, in 2005, you see Hubo come out of KAIST in Korea, and so you can see that there's a very different application of robotics in Eastern culture versus Western culture, in that they're primarily focused on these human-robot interaction sort of realm of dealing with what happens when we need to deal with people. And so KAIST is sort of like the MIT of Korea, let's say, the Korean Advanced Institute of Science and Technology, and they build Hubo, and you know, the applications that they're focused on are things like helping elderly people, and working with you know, human-like tasks. So Hubo in this example was taught to dance, but there are tons of different applications that they focused on, and you can see that they've gone right straight into the uncanny valley by putting an Einstein head on a Hubo. In 2006, PR2 is developed in Willow Garage out in San Francisco, Menlo Park, and their point is to build this robot that can essentially perform human-like tasks in both research and potentially commercial application. They shut down in 2014, and a lot of the code that they developed was eventually turned into the Robot Operating System, or ROS, and maintained by the Open Source Robotics Foundation. Some of the developments that they did early on in building these robots that were able to complete complex, like, manipulation tasks was pretty important in sort of pushing personal robots forward and making them seem more viable. Then in 2009, you start to see food service industry applications. So a company called Momentum Machines starts building this machine that they could use to make gourmet hamburgers. And so you really start to see an intrusion of robotics into every industry and field. And this is really interesting because whereas robots were primarily reserved in this academic environment or an industrial application, you start to see them creep into some fields that traditionally were manned by humans. And so, you know, as time has gone on, there's been more complex vision processing, there's been cheaper compute and cheaper components, and those have all sort of married together to allow robotics to branch into some of these fields that were previously reserved just for people, because labor is cheap and it doesn't seem like you should need a robot to do these kind of things. But you're starting to see those applications get more and more prominent in robotics. Then in 2010, you start to see commercial drones become available. So the Parrot AR drone is one of the very first, and you can see drones have changed a little bit since Parrot came out with this one. And, you know, this one was pretty advanced for the time. It had a camera. It could fly around with 6 degrees of freedom. It had its own IMU, so it could track pitch, roll, and yaw, and it could be piloted by an amateur. And it was in the price range that an amateur could afford it. In the 2010s, you started to see drones really take off as a toy, like, commercial product, and you start to see more and more commercial applications of them. 2011, the Robot Learning Lab at Darmstadt, which is a big university in Germany that does a lot of cool cooperative imitation learning robotics. And these are things that allow a layman to essentially teach a robot to do a task instead of having to have experts programming them to do the tasks and then figuring out ways to deal with all the error states and all the issues of, interfering with things or things being slightly misplaced. And so, machine learning starts to really start getting implemented in the labs. And now you're starting to see the industrial application of those machine learning techniques. This is, some of the very early application of that in 2011. Then in 2012, you see the establishment of the Open Source Robotics Foundation. The Open Source Robotics Foundation is a huge step forward in terms of taking a lot of robotics software development and turning it into something that is a shared resource, in that you're not having to re-implement like low-level LiDAR drivers all over the place, or you're not having to go and figure out some of the more basic framework for doing robotics projects. This was something that at the time, like pre-2010, back in the early 2000s, it was very difficult to find a substantial and useful code base that you could apply to your robots. And so a lot of roboticists were having to reinvent the wheel all the time. And the Open Source Robotics Foundation is an effort to compile all these tools and all of these standard things that you do into a framework that anybody can come and pull and work with, and then push back and have a repository on GitHub that allows you to work as one big collective robotics community in your software development. They also started developing a simulator called Gazebo, which would see a ton of use in the Darpa Robotics Challenge, which was a more recent challenge to build humanoid robots that could do complex tasks. And so Gazebo is great for doing complex physical simulation of robotics, and also trying to simulate real sensor input, which is hugely valuable in testing before you build, and cuts down the development cycles that are necessary to develop a functioning robot that interacts in the real world. Then in 2012, JPL put together Curiosity, which is a very large rover that they sent to Mars to study the composition of the planet and to explore, and also look at, what types of chemicals are present, and many other science tasks besides those. But it runs on what's called a radioisotope thermal generator for its power source, and it's a little different than some of the older rovers that use solar, because this will last a very, very long time and will give it power for decades potentially. So Curiosity is a huge step forward in the science that we can do on Mars, and it's also a huge step forward in just the way that it did its entry, descent, and landing, and some of the data that it got on the way in terms of the radiation data that it was collecting on what Mars transit looks like from a radiation perspective. And so it's really paving the way for human exploration of Mars and further probing to see if there might be life on Mars or indications of life on Mars. So Curiosity is a really huge progress in terms of robotics, especially interplanetary and space robotics. Then in 2012, robotics startups really forming up around the idea that you can bring industrial robots to every industry. And so Rethink Robotics is formed in an effort to make these collaborative robots like Baxter that can be used in factories and very easily taught new skills and applied to all sorts of different normal human touch labor type tasks. And the idea here is to start making robots as a product in the industrial setting rather than a tool that engineers use to develop very complex robot cells that perform a singular task. And so it's very much software and control focused, in that you're trying to make a robot that a normal human can program and interact with to do a complex task repeatedly. And this is, a push towards robots being a more general application. And they've had a lot of success in getting these Baxter robots in different applications in high-end, small batch assembly processes and things like that. 2014, you start to see swarm robots really take off. So swarm robots are interesting because they're sometimes tens or hundreds of robots controlled independently, and then they have network communications, and they can try and figure out how to do tasks collaboratively. Like in this case, these little robots that Harvard has made are used to right now just self-assemble into groups or move through barrier obstacles, things like that. The real challenges with swarm robots are how do you even build a lot of robots cost effectively, and the way Harvard solved it is pretty ingenious here. They just have little circuit boards with pin legs, and there's a couple vibratory motors that allow them to move in one direction or the other, and then there's some IR sensors and transmitters on them that allow them to communicate. And so this is one of the first examples of a swarm of over 100 robots that's ever been built. And they're starting to figure out algorithmic ways of having them communicate and navigate their environment as a swarm that give them some effectiveness that you might not be able to get in one or even a small team of robots. And so there's some really promising applications in swarm robotics that should be coming up in the next few decades. So then we're getting into sort of what really cutting edge robotics is focused on. So the Darpa Robotics Challenge is a huge competition where tons of international teams are coming together to solve very uniquely human and challenging tasks. Things like driving a small vehicle, getting out of it, navigating through an interior space, opening and closing doors, doing things like climbing up ladders, walking over rubble that might not be, predictable, stable, getting to things like fire control valves, using tools to do things like cut through a wall, or maybe picking up a person and getting them out of a dangerous space. And so, there's some amount of teleoperation, but there's also some amount of autonomy here. And there's many teams competing to perform all these tasks, and they're judged on a lot of different criteria as to how they perform the task. A lot of the robots haven't even gotten all the way through the course, but it's pretty incredible that these robots were built and brought to the competition in such a short amount of time. And, Boston Dynamics has been pushing a lot here. The lab I was in, the Romello lab, which is now the Terrestrial Robotics Lab at Virginia Tech, they brought their own hardware to bear. And then there's just a ton of other teams, like the Robotis teams are out there with Thor, and there's also a ton of Atlas, which is the standard robot that Boston Dynamics developed for the competition out there, and they're all working to sort of accomplish these same tasks, but also really push forward in terms of simulation and hardware and software what humanoid or similar humanoid robots are capable of. And what you're starting to see is these humanoids that are almost applicable in a general way, which would be a huge advancement in terms of robotics, because once you can get them to do these general tasks, then you can make them cheap enough and you can start replacing labor almost across the board. And so right now they're focused on search and rescue. I'm sure at some point DARPA will want to adopt them for military purposes, but hopefully the goal is to use them in a way that is peaceful and towards productive societal gains. So getting people out of dangerous situations, doing work that's dirty or dangerous that would normally cause people to get sick or injured, dealing with things like nuclear disasters, stuff like that. All right, so that really concludes the history of robotics. Next we'll get into some applications, and then we'll get into sort of what the academic disciplines are that are covered in robotics, as well as some components that you might see in robotics applications. And that'll really wrap up our intro to robotics. And I'll sort of give a little teaser for what the next course will be, which is CAD for robots. I'm going to go ahead and end the first half here. This is where the intermission was in the Crashspace presentation of this lecture series. And then look forward to part 2 being posted sometime next week online, and you'll be able to get a really great grasp on what the academic theories are that go into robotics, as well as some of the common components and applications of robots. And so thanks for listening. And I'm Kyle Cawthorn again. I really enjoyed researching all of this and getting it together in a class format for people. And I really can't wait to get to the parts where it's all hands-on and I can teach people some of the skills that I've picked up over the years. So thanks for watching, and I'll see you on the next one. Be sure to like and subscribe. Got to get that in there. And have a great day.
Noise you couldn't quite locate or explain. Couldn't quite locate or explain. Noise you couldn't quite locate. Noise you couldn't quite locate.